Hi there, good morning. And today we will continue with Ionic equilibria. If you look at the main syllabus here, we have finished on explaining the terms pH, Ka, pK, Kw, and we also finished calculating the pH of strong acids and strong base and using Ka and pK and Kw. All right, now we will skip to this two parts here before we do titrations. All right, here, G and H. I'm probably doing G one video and H another video because calculation quite a lot, okay? So today, first one, I'm going to explain how buffer solution control pH. Of course, we first ask, what are buffers? Okay, buffers, and you can see, right? How many times are 2, 4, 6, 8, 10? About 10 times they ask what are buffers. Let me show you the question. It's no problem, see? Right? See, so. Explain what is meant by the term buffer solution. Okay, another one, page 3 here. Another one. What do you understand by the term buffer? Okay, another one, page 6 here. I can go on forever. Okay, what is meant by the term buffer? Okay, now. So you need to define what a buffer is, which is the first part here, what are buffers, and then second one, how does, actually the second one is types of buffers, types of buffers. Now there are two types here, one is acidic buffer, and one is basic or alkaline buffers. All basic buffers, okay? We won't call it this name, but it means that, okay? Of course, that one is how do they work? Okay, how does buffer solution control pH? Okay, how do they work? How do they work? How do they work? You need to know the equations, okay? And because fourth is, well, the pH of blood is separate, okay? And fourth is, of course, calculate pH of buffers, okay? Right, so we look into this now. Now, how, first of all, definitions. I put down here in my, well, the total notes here, definition. You can adjust it, right? Now, this is from the book. They are buffer solutions are solutions. No, they're not solids, they are solutions. Not solids, they're solutions. It means aqueous. They are solutions where the hydrogen ion concentration, or can you see the pH? Hydrogen ion concentration will remain fairly constant or resist. Two ways to put it. One will remain fairly constant, not constant. You constant wrong. Okay, remain fairly constant. It will change a bit, 0.01, 0.04, whatever. Or the pH resists pH changes. Okay, that's the first mark here. Okay, first mark here. The pH remain fairly constant or the pH resists changes. Two, when a small amount, very important, this one, small amount, because large amount will change a lot. A small amount of acid, or I like to put strong acid, okay? But marking scheme says when a small amount of acid or base is added. Okay, now let's look at the definition first, because this has come up so many times, so actually you should know. Okay, now first one here. I got all the marking scheme here. You can refer to it if you want. So make sure you memorize this thing first. All right. So here the first one is 2004. Okay, very old. Explain what I mean by the term buffer. Right here you can see a solution that resists changes in pH. Okay, resists changes in pH. Yeah. Okay. See, blue lah. Resists changes in pH. See, no pH change. Wrong. Salah ni. When small amounts of H plus or acids or bases or alkalis are added. Okay, you must say when they're added, after you see when you put this acid and alkali, small amounts into water, the pH change about 4 readings. Okay, next one here can see what do you answer by the term buffer? Let's see the marking scheme again. Right, see when the solution resists changes in pH. The controls pH changes. Okay. Again, first mark is here. See, second mark is when small amounts of acid or base are added. Okay. So second mark is small amounts here. Okay. or pH remains fairly constant. pH remains fairly constant, not change, fairly constant. Okay, let's get another one. This is the best one, I think, page 18. I put down here page 18. Let's get page 18. Where's page 18? Let's off this first one. Page. Okay. This is, I think, the best one, right? Okay, explain what is meant by term buffer solution. Okay? See here, a solution that resists pH changes. So I like it. Okay, resist changes in pH. Okay, or you can say, okay, or small amount of changes in pH. Okay, right, and small amounts of H plus. So the same. So the 2 marks here, remember, right? A pH remains fairly constant. Or pH, the one is remains fairly constant. So seems to be pH resist changes is the most often used, right? So these are the 2 things here. Now let's go back to main notes. So what kind of buffers are there? There are 2 acidic buffer and of course alkali buffer. You can see here, I put down alkali buffer. 2 kinds of buffer, which means alkali buffer, the pH you can use when the pH is bigger than 7. For acid buffers, okay, the solution, the pH is less than 7. 4 or 5 or 6, whatever, okay, around that region, okay, 4 point something. Okay, so you can see after there's a lot of examples. So now how do you make an acidic buffer? Very simple. You must have a weak acid, not a strong acid. You see after a while, okay, weak acid. What is a weak acid? It will ionize partially, okay, ionizes partially. Okay, I put down here the 4 things about buffers. What are buffers? Different buffers. Okay, types of buffers. How does it work? And calculate pH. So we do the first 3 today. Okay, this one I think we did now because a lot of calculations on. Okay, weak acid and the sodium salt. Normally sodium can be potassium also. Why? The sodium salt. Why all PAS salts are soluble? Isn't it? Solubility loss. Or it means that they will totally soluble. Right? You need to be totally soluble. Both of them are soluble, right? But this is unionized. So like here, right? My first example is of course the famous example of ethanol acid and sodium ethanoate, right? So this, remember this fellow here, okay? You put the equation, they will ask for equation 1. Okay, of course equals okay, it's reversible. Why? Because it's partially ionized. CH3 COO minus equals plus H plus. If I've got time equals 0, is 1,000 molecules here, is 0, 0 here, and time equals equilibrium, only about, let's say, 6 of them, or 10, 10 of these fellows will dissociate. So how much remaining is 9, 9, 0. Here's 1, give 1, so here's 10, and here's 10. See now, it's a very small amount to me. That means most of it is this molecule. And this fellow here won't change the pH. Why? Because pH is equals to what? pH is equals to minus log base 10 what? H plus. See now, this is not H plus. This is a molecule. So this fellow here, if you have high concentration of this one here, the pH won't change. It is this fellow here that causes the pH to change. Because pH is a measurement of the concentration of H plus. So the second one, of course, is my base. Sorry, they can call it base actually, but it's a salt. Sodium salt of this acid here. Must be of this acid. The side you see after it's called a conjugate base. Okay, now this is solid, right? Of course, in aqueous, it will give you one direction. That means that it is totally dissociated. Okay, to CH3, COO minus aqueous plus Na plus aqueous. That means if time equals 0, I've got 1,000 molecules here and it's 0, 0 here. At time equilibrium, that means it's totally is 0 here. No, there's 1,000 here. It's 1,000. Now this one don't. It's just a spectator. Okay, but this is important now. Now, remember this and this are the same. See, right? Now remember I told you if this is an acid, this fellow here is a base. Why? Because it can go backwards. It's a proton acceptor. Right? So these two are conjugate pairs. Conjugate pairs. Okay? Very important. It's a base. BASE. That's why this is actually a salt of this acid. But sometimes this salt is also called, they refer to it as a base because same what this and this. They don't want the Na plus only. So, but I like to call this one is a salt. Okay? So this is how it goes. That means there's plenty of both of this. There's plenty of the conjugate pairs. Plenty of the acid, the unionized acid, and plenty of the salt, the conjugate base, which comes from basically from the salt. Didn't come from the acid because the acid only ionized a bit only one. So the concentration of this fellow here, okay, come mainly from the salt. You can control the amount because it's a salt. You can weigh it out, okay. Now, of course, then you have got your. Now this one, remember, it come out a lot of times. Now H3PO4 is a weak acid. Okay, I just show you here. Okay, now H3PO4. See, it's used to be very popular last time in titration, but now because it's pretty hard, I did it's a 3-step phase change. See, PO4, you can ionize to give you the first Ka. K1 is H plus H2 PO4 to 1 minus. And this fellow here, right? H2PO4 is dihydrogen phosphate. Okay, this trihydrogen phosphate is called phosphoric acid, by the way. You've done it in Form 5, remember that? Of course, forget that. Phosphoric acid. This is your dihydrogen. It's called dihydrogen phosphate. Okay, because of 2 hydrogen here. And this minus fluid can also dissociate another Ka2. H plus H PO4 minus is mono hydrogen phosphate. Now, the third one, of course, H PO4 minus is 2 minus, 2 minus. Can also undergo another one, Ka3, to give you H plus and PO4 minus. So interesting, of course, this fellow here, they'll ask you also later, you can see, if it goes back here, this is a base. This is acid. It means this fellow here, I'm going to put blue, right? A mixture of this fellow here and this fellow here can form a buffer. Okay, but this fellow here must come from sodium salt. That's very small amount here. So if this go backwards, this acts as a base. Now you talk about this fellow here. If you go forward here, that means it acts as acid. For this equation, it acts as acid. That means you must know which equation to write, because why it's a proton donor. Okay, but this is the most famous one. So here, most famous one. You can see afterwards this pair. This, of course, is a conjugate base. Okay, and in the buffer, this comes mainly from the salt. The sodium salt is actually called Na2HPO4. This is called disodium, actually. It's called disodium, if you want to know the name. Disodium hydrogen phosphate. Okay? And this also come from a salt. No, it's called acidic salt. It's monosodium. Okay, this disodium H2PO4 is monosodium. Monosodium, okay, hydrogen phosphate or dihydrogen phosphate. Okay, these are names. We used to do this or are practical. All right. Of course, this one here, remember this one, this is your acid, and this is your base. Of course, this fellow here, I put green color. Oh no, sorry, this one. Green color, come on, green color. Right, this fellow here, and this fellow here, same, isn't it? Right? This fellow here can act as an acid or base, same as these two fellows here. this fella here. So you can see how an equation will tell you whether the fella can act as a base or an acid, depending on who it's reacting with. After you see all this coming out, they will actually test you heavily on this. So you need to know how this got 3 hydrogens. That means that it can undergo 3 Kas, right? Ka1, Ka2, Ka3. Okay, use your brains a bit to see how it can work. Okay, now, so you can see here, I say that these two are conjugate pairs. And they are in large amounts. That means that they are ready for action. Now, how do they react? Okay, how do they react? How do these two, they'll ask you, how does this and this now? These are the pair, these are the buffer. The buffer will contain, the buffer solution will contain the weak acid. Okay, normally it's about the same concentration or a bit more. And of course, the sodium salt. Normally sodium, they don't use potassium, but even potassium can, because what you call spectator ion. Okay, so normally this is like 0.5 moles and 0.5 moles, same. So, but this one is hardly dissociated. So the conjugate base come from many from here. Okay, so how do they control the pH? Okay, now I'm going to show you the theory first, okay? Right, how it works. Now I'm going to use well, this way here. Okay, something to, let me see, is this one? Oh, is it this one here? Okay, that's the one. I thought got one more here. Nope. Here actually, yeah, this is more, well, more down to earth, but let me explain something first. All right, so you can see how it works. They ask you, maybe I show you the question. Never mind, wait. I look for the question first. I will stop it, pause for a moment. Okay, I found it. All right, now here is a 09-4. I got answer, but I forgot to cut the question. Write suitable equation to show how a mixture of ethanoic acid, yeah, it's a weak acid, and sodium ethanoate acts as a buffer to control pH with either acid, should be a small amount. After I'll explain a small amount, okay? Here it says, right? Okay, a small amount should be when a small amount, okay? So we can say now of acid or small amount of alkali is added. So they ask you for suitable equations. So what happens? Right? Very simple. Let me show you the marking schema. See, hold on here. Now see, remember in your here's your buffer. Equals, here got thousands of CH3 COOH. Okay. Now remember I told you this over here, equals here will dissociate a bit only, because the weak acid to give you CH3 COO minus equals plus H plus. Okay. And then number 1, number 2, of course, your sodium ethanoate. Okay. Equals here will give one direction. CH3 COO minus plus Na plus. I told you that if there's 1,000 here, what remains is 990 here. So here's 10 here and here's 10 here. Right? Right? This is at equilibrium. Now this at time 0, this time 0, you're going to put here. At time 0, this is 1,000 of them. How many 1,000? I put what? I weigh out and put inside what? I control the whole thing, is it? It's 0, 0. And at equilibrium, 0 and all 1,000 here. 1,000 here. So in this whole thing, I got plenty of red color, got plenty of this fellow here, which is this one here. I got 919 molecules. And inside here, I got plenty of this one here. I got this one here. I got 1,010. So these two are the main thing that will help keep the pH almost fairly constant or resist any attack of alkali added inside. It means OH minus added inside. Add OH minus inside. Or I add any H plus inside. Remember, it's a small amount. Let's say a small amount, how much? Let's say 50 lah. Okay, I put 50 of them inside here. Or 50 inside here. Okay. Cannot go over there. All right, it's 2 months, it will change. So what happens? Now I put, remember here inside got a lot of this fellow here, and a lot of this fellow here. This one is the same now. Okay. Okay. The conjugate. This is a conjugate acid. And this is your conjugate base. They're from each other. Conjugate. That's why it must be, they can go forward and backward. So let's say in this case, I add 50. Here I put 50. Okay, of this one here. External. Masuk down. Okay, from somewhere here. Okay, put inside here. So now 50 will actually cause a great pH change. After I'm showing you the calculation again, it will cause a great pH change. So how do this fellow here react with this one here so that it will be nullified? It will cancel off the effect, right? So that means there must be an acid available to act here. So who is the acid? This fellow here. It's an acid now. So the acid here will react with this one here. So now remember I got 990 of them here, waiting to destroy this fellow here. So after added, okay, that means 50 of them will react. So after reacting here, so gone. How much is that behind? Okay, how much is that? 940 left behind. All right, and here is what? Here will be 50, and here is 50 now. Okay, right now. That means no more is on here. That means the effect is gone. That means it will not change the pH. This fellow here won't change the pH as well because it is not H plus, okay? And this also won't change. So the pH is held constant. So this is the equation to show that the acid, the weak acid there, which will now dissociate itself to react with the alkali. Okay? So this is how they cancel off the effect of the OH minus. Now, if you add as H plus, 50 of them here. Okay? Right? 50 of them here. Right? Now, remember this, I put green color. See, this equation is reversible. This is one way. This is reversible. I know. Okay. So remember, here I got in the equilibrium, I got 990 of them here. Here got 10. Here got 10 H plus. Now, when I add this 50 H plus inside here, suddenly this will increase to 60. According to Le Chatelain's spin, what happened? It will shift backwards. Yeah, right? Equilibrium position, equilibrium because reversible, it will shift backwards. But then to go backwards, according to this equation here, I must have a number 50 of this one here, but there's only 10. How can? Not enough, is it? So who comes to help? This is the same one. It's on here. From this part here, actually they're not 10. There's 1,010. See now, there are a lot of them here. Waiting, the same species, just the number is bigger because the salt supplies on here. So I got 1,010 to kick off the 50 here. Kick it off. So how will it react? So the 50 here will plus this your conjugate base here, which came from the salt mainly, and go to here and shift back here. So this is the equation they write. Okay, so now this acid is formed. Will this acid, this is a molecule, will this molecular acid here change the pH? No, because it's undissociated. See, I said pH here is equal to what? It's equal to log base 10 H plus. This is not H plus, unless it dissociates, but it's very, very small only. So this one won't change the pH. That means the effect of the 50 H plus is being destroyed. So that means the pH remains fairly constant. Yeah, so these are the two equations they ask you. After you see, now I'm going to work through the whole equation for you. I'm going to let you see actually how it's being done. Okay, so now this, as I said, is how the thing works. All right, so equations are important. The main equations are, as I said, this one here, this one here, when an acid is added, they want this one here. When the alkali is added, when the acid is added, the conjugate base will come to play the part, which came mainly from the salt. Okay. Now, if an alkali is added, an acid will come to destroy it, which came mainly from the weak acid. Okay. So these two equations here. Right. Now I want to don't go to alkali buffer. So I want to show you actually how to calculate it. As a simple calculation first. Okay. Now, to calculate pH and buffer is very simple. Remember, pH is made out of two things here: the weak acid HA right? HA, of course, in this case here is CH3COOH. That means this is your A, right? This is your H. But they put Ha, okay. And this is your sodium salt. This one, of course, is your CH3, COO, and A, right? All right, so remember this is one equation, this two equation. So, okay, so you mix these two together and you form your, inside here, this inside here, this inside here, you form your buffer solution. So they will go up and down, go up, and of course, this one here will cause it to go backwards, okay? And so it comes to an equilibrium. So inside here, you got plenty of CH3, COOH, plenty of what? Plenty of CH3, COO minus, okay? Plenty of Na plus, which is no need to talk about, okay? And of course, you got some H plus, which came from here, okay? That's why this one, the pH normally is not very low, but about, 4 point something, 5, whatever, okay? Right? Because of the weak acid here. Now, to find the equation to do calculation on the pH of a buffer, remember, you have to go back to original Ka here. You can only use Ka because it's the only one that is reversible. It's not reversible. Okay? So Ka is equals to, of course, constant of H plus and some here, A minus, Got it? So you brings up here, you brings down here, you get H plus equals to Ka, so forth, okay? Right? Remember this thing here, this whole equation here, this is the constant of your whole solution, of your whole buffer solution. Understand now? Right? So now here, right? So Ka, okay? Now here is your A. Now A minus here come from, mainly from where? From the salt. That's not, right? Because the salt, and I just completed the A minus came from the acid, is only very small. Now this is also mainly from the acid only, because the acid hardly ionizes. So H plus is equals to this, all right? Okay, so now I got so I put acid here and salt here. So I now log the whole thing. This log H plus, okay, equals to log base 10, all base 10, base 10 Ka plus log base 10 acid over salt. Now to make it nicely to pH, I put minus here, minus here, minus here. So it becomes pH. This is put red color. This will become pH. Equal to P is minus log 10 K, so pKa. Now I put a positive sign here, so I just invert here, log base 10. I put salt over acid. Remember, this is in moles per dm cube, okay? That's why now this is the main thing. This is the main equation to find the pH of the buffer. This is the sort of salt. Now then this is the salt concentration here, or they call it the base, the conjugate base, also can over the acid. Okay, so now this is the whole thing here. Right, I'm going to stop for a while. Okay, now let's see how we're going to use this equation here to show you that if you add a small amount of acid, small base into a buffer, there's hardly any change. Okay, to prove to you, we want to talk about buffering capacity, means how much the buffer can take. You add 10 cc or 1 cc, with 20 cc, then the bubble will break. The whole pH will change drastically. It means the capacity to withstand the amount of the acid added. Normally it's strong acid, okay? So you can read this by yourself, okay? And so forth here. Now, I just want to show you here, I did something here. I thought it was pretty good. This I think used in one of the books I copied from this book. Mr. Lai is no smart boy. I mean, I just learn from people. You don't want to be smart, you just have to be clever. That's all. Take from people. I mean, people are so smart. People have learned so much things already. What do I know, man? I don't know how. But I think, wow, people do this. It's pretty good. Help me to understand. So I share with you. What I learned, I share with you because it makes you smart. So you can score my A star for me. Otherwise, I'll slap you. Okay? Now, calculate pH of buffers when acid and base are added. This is a very simple thing to show you. Okay. Now let me explain. So I've done my homework already. So I prepared this about 4 or 5 hours now. I tell you, you fellas, never give a good light key for this, so you idiots. Okay, now my God will repay me. You fellas will not repay me. I can repay me, get A star, okay? A star, A, no B and C, a deal of donkeys and cows and idiots, okay? I don't want it. Calculate the pH when 1 cm cube of 1 mole per dm cube of HCl is added first second 2 was added to 1 dm cube. What does it mean? What does it mean here? It means that here I've got originally I got my 1 dm cube here, okay? 1 dm cube of water. All right, this water here, the pH is what? pH is 7, isn't it? Okay. Why? Oh, you don't know why, KW, you idiot. It's H plus and what? OH minus equal to what? 1 to the power 14 is it? Oh, no. Okay. It's same as it. So x is it. So x squared is it. So x is equals to 10 to the power of 7. Okay. 1. Side pH is this one here. Okay. This pH of water, neutral. Neutral. Okay. So let's say if I add inside here, the first one of course is add 1 cm cube. Only 1 cm, say small amount, you know. Small amount, I say strong acid, no. Okay. So I like strong acid because but the definition in all the definition for your CIE, they say just add acid. Acid, don't care. Okay. But I prefer strong acid because strong acid will really cause a change, you know. Okay. 1 mole strong, okay, strong acid. Okay, so I got here, okay, here 1 cm cube of 1 molar. So now this one here, I want to find out how many moles of HCl there, right? So MU 1000, so 1 times 1 is so it contains 0.001 mole, okay? Okay, now this is of HCl add inside here, right? So you can see from here now, all right, here. Well, here, okay? So now number of moles of here, number of moles of H plus added is 0.001, okay? Here, 0.001, 2 zeros, which is in 1 cm cube or 1 molar HCl. Okay. Now, so the total amount of H plus in my beaker. Okay, remember here's my 1 dm cube, 1 dm cube of water. Okay, it contains your H plus how much? It contains a concentration of 1 times 10 to the power of minus 7. Okay, it's original. So now I plus, okay, inside here for this 1 dm cube, I plus another, now here got so many moles, I plus how many moles? 0.001 mole. No. So the total is 1, this one here, plus this one here, is equal to R, this one here, about the same. Why? Because 7, see, minus 7 is what? Is 6 zeros, isn't it? 1, 2, 3, 4, 5, 6, 7. This is same as this. Plus 3. It's 0.123. This plus this is equal to this whole thing here, which is approximately, is 2 many zeros here. Forget it. So approximately equal to 0.01. It means this one here will count a lot more. So this is equals to what? 1 times 10 to the power of minus 3. So now it's per dm cube. So it's moles. Why? Because 1 dm cube of water, isn't it? I use one per dm cube. So now this is the concentration. So I put here, pH is equals to, right? Here, isn't it? Right. So what is it? Equal to 3, no. That means change from 7 to 3, man. A lot. 4 units. If I put in water, the water change from pH 7 to pH 3. 4 units change just by 1 cm cube of the strong acid. Now, if I put alkali inside here, say, here I put down here, all right? I put blue now so they can distinguish it, okay? Blue. Now, 1 cm cube of 1 molar of NaOH, okay? One is strong, small amounts of a strong base. Same thing here. Number of moles of NaOH is MV over 1000 is 0.001, of course. Same thing, okay? So here, right? So remember here, pure water, right? Okay, OH minus, right, is this one here. Remember, same as H plasma, okay? So the number of moles of OH minus added is 0.001 here. So the total number of moles of OH minus added is how much? Total number of moles total, right, is equals to 1 times 10 to the power minus 7 plus now 1 times 10 to the power of minus 3. Same as the acid, right? So it's 0.123456 plus 0.12, okay, which is also equals to 0.001234 and 1 here. So it's approximately equals to 0.001, okay? Okay, so this is my OH minus, right? Over 1 dm cube, 1 dm cube. So this is the constant, this is the constant. Okay, so in this, after everything inside here, so what is the H plus? Because pH is equal to H plus concentration. So here, bring over here, and your H plus is bring over here, right? Bring down here, it's over now, down here be 1 times 10 to the power of minus 3. So cancel here, you get 11. So what is it? So pH is equals to, here, pH is equals to, okay, minus log base 10, and of course 1 to the power of minus 11. Okay, bring 11 down here, minus 11, of course 11. So the change again of 4 units there, when you put a base, see not, pH changed drastically. Only one cm cube of acid or base added. Now let's see. How about now add the same thing into a buffer? This is the test. So I do all for you, easy for you to see. So I got here a buffer made of, okay, here's 1 dm cube, okay, of this acid here. So here, original, here's 1 dm cube volume of this 0.01 mole per dm cube of what? Of my weak acid, okay? Ethanol acid, right? Now I got here my salt, this one here. 3.2 grams of sodium ethanoate. Okay, why 3.2? I don't know what this question says. Okay, 3.28 gram of sodium ethanoate. Okay, clear not? I put inside here. Once I make become buffer already, what? Because I got my weak acid and the sodium salt weak acid. Okay, so they ask you what's the pH of the buffer, given your Ka is on here. Okay, now so I found that the amount of this photo here is 62. So 3.28 over 82, not 62, 82. I made a mistake the first time I calculate again. It's 0.04. Why more per dm cube? Because I put in one dm cube. So this is 1 dm cube. So this is the concentration of my salt. It's not my salt. Okay, concentration of my acid is this one here. So I can put down here. I use the formula. pH equals to, now very simple. pH equals to pKa. SA, South America, I always say South America. SA, South America. This is how I remember. Okay, I always remember this. Famous for is what? For is football, isn't it? South America. Okay, South America. Okay, positively South America. All right, easy. So I put down here the Ka is equal to this one here. So I minus log base 10, 1.84 to the power minus 5 plus positively log base 10. So 0.04 over 0.1. Okay, so I do my calculation, my maths. You don't have maths, go back to form 1. You for this here. See, okay, log it, bring here minus 5, so it's 5.34. So the original pH of this is equals to 5.34. Okay, now comes when the pH of the buffer, what will be the pH of the buffer if the 1 cm cube of 1 mole of HCl? Same. No. That means inside here 1. That means I'm going to add like the sound here. All right, I'm going to put down here red color. Okay, first I got here 1 cm cube of what? 1 molar HCl. Taro is not here. If I taro into the water here, it changed from 7 to 3, isn't it? If it change here, how much it changed? 5 point what? 5 point, here's 5.34. 34. It's supposed to stay fairly constant, but wow, you see, here it changed 4 units, no? If it changed 4 units, habis lah. But how much did it change? Go inside here. Remember, the number of moles of your HCl here is equals to 0.001. Okay, calculate already earlier. Okay, so of course, here we'll give you H plus, same. Number of moles H plus is also equals to 0.001. All right, now, so what happens now? Now, before and after, I always use a before adding HCl and after HCl. Adding how much? 1 cm cube of 1 molar HCl. Now remember the ratio of these two. What these two called? Now this is your acid. This is called your base. This is a conjugate acid. Conjugate acid. This is called the conjugate base. Of course, this you can say it's a salt, okay, or base. This is your acid. Okay. So now when you add acid inside here, when you add, now remember before you add the acid inside here, what's the concentration of acid in the buffer? In your buffer. Okay, right? These two are your buffer. Okay, remember why? Right? See, or not? Number of moles is in 1 dm cube, isn't it? So this number of moles of acid is 0.01. So number of moles of acid is 0.01. Okay, in the 1 dm cube. Okay. So now you add HCl inside here. So the number of moles of remember when you add H plus here into your buffer, who will it react with? Our friend, this fellow here will come to take it out. Right? So it will be 0.01. Okay. 1 here. So 0.01 here. Right? Will react with my conjugate base. This will come to rescue. Originally here was 0.04. Why 0.04? There, here. Here. Okay. Yeah. So they come and they will react. Plenty, 0.04 and 0.01. It will form, of course, your ethanoic acid. It will come to take away the H plus. How much form? 0.001. So how much is left behind? It will be 0.04 minus 0.001. How much is it? 0.039. That's why I said, look here, it means this one has increased. It means after adding HCl, the concentration of the acid will be 0.1 plus this one here, which is this one here. Now the conjugate base or the salt here will be 0.0 minus this 0.01, which is vectors. Yeah. Okay. Yeah. So it's 0.09. So now this is after adding your 1 cm cube of HCl. So this is the actual concentration now of your weak acid. This is your salt, or the conjugate base. So now I substitute into find the pH now. Okay. So the only thing changed is the concentration of your acid and your conjugate base. That's why people put base here and this acid here. Okay. But let's put salt because it comes from the salt. So pH is pK, positively South America. Okay. Salt. Okay. So now this is 0.039 over this 0.1. Okay. 1 month now. Okay. So 5.28. That means from here, which is your 5.34, 5.34 has gone to 5. It means a very small amount change, a small change. It didn't say don't change, it will change. Of course, with acid it becomes less than, okay, 3.3428. Change about how many units? 5.34. Let me do a calculation. And this is okay. 5.34 minus 128. Only 0.06 change, 0.06 units. Okay, so the thing remains fairly constant now. How about you add alkali inside here? Same thing, right? Remember, when you add alkali inside there, right, who will come to the rescue? Your acid. Okay, how much was the acid of, this is the buffer. How much was the acid in the buffer? Is 0.01. Okay, okay, so remember, this was the original. I put a blue color here. Original one, of course, is 0.01. So you add from the 1 cm cube is 0.001. So out of what is plenty to react up. Okay. So of course, what is formed? Of course, when this react here, the H plus will react with this one here to form water. That means 0.001 water here. And of course, when this one come out here, this is formed. Your base is formed. But of course, this one will reduce to how much? Will reduce to 0.01 minus 0.001, which is how much? 0.009. It means the amount of acid left behind will be 0.009. See, minus this is the one came from your which minus not. Okay. After adding what? 1 cm cube of 1 molar. No. And of course, this is your base. What will increase because this one here plus now the 0.04 here, which is original found in the buffer. Okay. So now I got 2. The 2 ratios of these 2 ratios are very important. Okay. So my South America. Okay, South America. I put inside the equation, which is what? pH equals to minus pKa positively log base 10 South America salt over acid. Okay, or base over acid. Okay, same. All right, so salt is what? Or base is on here. Right? Acid is on here. You do the calculations, blah, 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 you get 5.39. Hardly change at all. Okay? Here's how much? Original how much? 5.34. 5.34. 5.34 go to 5.38. Okay? Which means about 0.05 change. Of course, become higher because alkali don't. See now. It means it resists change. You got it? Right? So that's how a buffer works. Right, the 2 conjugate pairs, right, the acid HA, right, which will give you your H plus and your A minus, your acid is no, and your sodium NaA will give you straight away your Na plus and your A minus. These 2 fellows are same, so these 2 fellows that are going to be the main key player. This fellow here will react with any addition of alkali to cancel out the effect. This fellow will have any amount of H plus here to cancel effect, and some will give you a HA. So HA will increase, but it doesn't change the pH because pH is equals depends on H plus concentration, not the undissociated acid. Okay, right? Now I'm going to go through later here. Okay, I'll go through first. I'll also with you lah. I say about 5 more minutes. Okay, now here, look at here. This for alkali one. Now, alkali buffers are very simple. They are formed when look here. I think I got that down here. Okay, alkali buffers are formed when a weak base must be a weak base plus also partially dissociated. Remember, because like for example, ammonia NH3 plus water. You must put this equation down. No, H2O. Give you what? Partially only NH4 plus because the base it will accept a H plus not plus OH minus. That means this is very small amount. Large amount is here. Okay, let's say 1,000. 1,000 here, right? Here is 0. Here is 990. Let's say okay. Then no need to put okay, this will be 1. This will be 10, and this will be 10 only. See now. Partially dissociated, okay, right? And of course, it must be the salt of the base and the strong acid. The base, this base here, okay, ammonium chloride or ammonium sulfate also can, or ammonium nitrate. That means that it must react with HCl or HNO3 or H2O4. Okay, so it must be a strong acid. So the salt, why? Because then it will be completely dissociated. And then it's normally used give you NH4 plus Cl minus. Okay, therefore this one here is 1,000 here. At the beginning time is 0, and it's 0 here. At time equilibrium is nothing here. This is completely dissociated. Why? PAS salts are completely soluble. So this is 1,000 here. This 1,000 here. This is your what? Spectator ion. So basically, plenty of base, plenty of your conjugate acid. This is a base. These 2 are your, remember, this is a base acid. So, of course, these 2 here. And that's how they react. Okay, now here, I'll show you how they react here. Okay, then we in. Okay, remember, now this is your base. There's 990 here. Okay, and this one here. Okay, so now this is a normal one. Right? It's not completely same. So this is 1,000 here, and this is your 10 here and 10 here. So Remember, this is large amounts, this large amounts. So base, this is conjugate base. So conjugate what? Acid. So when acid is added, right, who will come to rescue to clear away acid? Of course, the base. All right, and it's straight. Yeah. Right, plus one here give you ammonia. Sometimes some people also talk about plus H plus. Can also. Example 50 here, right now, you have 10 and then you will cause this order here will shift forward and will produce more. So some will go down, same thing, some will go down, this one will increase to this one. But normally this is the best deal, okay? Ammonia by H plus. Okay, so cancel off the effect. And if alkali is added, very simple, alkali is added, this is an acid, give here to form ammonia. Ammonia won't change the pH, right? It is undissociated. Okay, there's no H plus here. So these two equations are the one they will use to ask you, right? To show you, well, the effect of it. Now it came out. I'll show you the question, okay? And then we end. One more after. Okay, here. A solution containing ammonia and ammonium chloride equals as a buffer, resisting change in pH when applied. Explain with the help of equation how this mixture acts as a buffer. Very simple. See, I put down here when a base, when as a base, it means they will act as a base when acid is added. That means the base here plus H plus give you ammonium ion. Okay, and as an acid, base added. Okay, now this is the marking scheme. Say ammonia NH3 plus give you some here. It means acid is added. The base from the buffer is here. When the alkali is added, this is the acid. This is the acid. This is a salt, isn't it? From the salt. This from the what? This from the base. See? Okay. See, 1 mark each. Okay. So we are just on time. We are finished here. So I will see you later. I will try to do one more on calculation, all on calculations. As I said, so if your maths are poor, I tell you drop chemistry. Physical chemistry is all on maths, log and whatever. Okay. So I see you goodbye for now, and God bless you. Stop this. Stop. Okay, stop recording.